Hello, am I audible? Hello, am I audible? Okay, okay. Thank you. So, good evening to everyone present here. So, we shall carry forward our discussion, which we did till last Sunday, last class. So, basically, in the last class, what we did was we basically tried to study the basics of concrete, basically, what is concrete all about. Okay. So in this class also, we will be, we will be going little deeper into the basics. We can say that to be the part two, okay, second part of the basics, so that when we will be going to the special concrete part, it is easy for us to understand the mechanisms which are happening there. Okay, so that is the main motto of this week's class. Okay, so let us start then. So yeah, so basically we will be going a little deeper into the fundamentals of proportioning in the concrete mixes, and we will review various things which are undergoing inside. Okay, so what we learned in last class is that like cement is basically the paste. Okay, it is a suspension of cement in water. The mortar, as we know, is a suspension of the cement paste in sand. Okay, or sand in paste. The concrete is a suspension of coarse aggregate in mortar. Okay, so basically what we found in the last class was that concrete was a composite, is a composite whose properties are related to the constituent materials. Okay, so basically sand, cement, aggregate and water. Okay, they define the properties of the concrete. And what we also learned was that the main reactive components, okay, the hydration components are basically done due to the existence of the cement and water constituents, or otherwise we can say like fine and coarse aggregates are just the inert particles which are used as fillers. Okay, so our motto is to find out the issues related to constituents, proportioning, properties, method, environment, construction, etc. Okay, as we all know that these all the properties are interrelated. Okay, so our basic objective is to find a suitable combination of sand, water, coarse aggregate and cement in various amounts, okay, which are relative in nature, so that we get fresh and hardened state properties which are adequate, as well as meet the durability and other requirements which are dependent on the structure and the environment. Okay, so that's what we like, our motto is we should go through the basic concepts based on these criterias for concrete, uh, that will be useful in the coming lessons, in the coming classes. So it's important to understand the proportioning basically of the admixtures and the constituents. Okay, so that is what today we are going to go through. Okay, so the basic concepts which we will be discussing today are basically these four. Okay, firstly, we will go through the water slump relationship. Okay, secondly, we will go through the characteristic and target strengths in the proportioning concrete mix. Okay, which is used basically in the mix design. Thirdly, we will go through the water cement strength relationship. Okay, and fourthly we will we will go through what is this term. Okay, it is called S by A. Okay, this is a term which has been coined. So we will go through what are all these topics, and what are its effect on the behavior of concrete. Okay, so if we see this, this is a plot between slump and unit water content. Okay, yes, okay, I have not shared. Sorry. Is it visible now? Okay, thanks, huh? Okay, so let us if we see this, it is a plot between slump and unit water content. Okay, so basically we can assume the relationship between slump and unit water content to be a straight line. Okay, and if you see, like, there are three lines drawn. Okay, so which are having different types of slope. Okay, this is because the properties, okay, of properties of the aggregates, okay, such as the size, particle distribution, etc., they determine this slope. Okay, so for variation in properties, the straight lines which are drawn will be different, and for this we need to carry out various tests. Okay, so that will determine the actual material properties. Okay, and it will help us in determining the variation of water content over a range of appropriate this one slump, okay, for a particular application. So this is what we have discussed, all like what we discussed now. This has been written here. So for a given set of material and properties, the variation may be taken to be a straight line. Okay, so it is not a straight line, but it is almost somewhat related to a straight line, and it is almost similar. Okay, so that's why we can say like slump is a function linearly dependent to unit water content. Okay, so now let us come to compressive strength. Okay, so if we consider like we are we have cast samples of concrete, okay, which are similar in properties. Okay, so that's why it is written here same concrete. So if we are casting same concrete, okay, so if we draw a plot, okay, with the number of samples and strength, okay, so we are likely to get a normal distribution. Okay, provided the properties, all the properties are same. Okay, so this normal distribution, okay, so as we like we all have studied in our UG classes that this normal distribution basically consists of two things. Okay, one is the mean, that is the center point, and other is the standard deviation. Okay, so the standard deviation basically represents the the spread of the distribution, or in our terms it's the variation which is used for quality control. Okay, so that's what we can see. This concrete is characterized by mean strength and standard deviation. So uh, what we can say from this is, you know the these two strengths, okay, the mean strength and the standard deviation, these two parameters basically, these are the main properties, okay, which determine the compressive strength of the concrete. Okay, but that is the over it is an oversimplification. Okay, majorly these are the two parameters, but it has some sub parameters also. Okay, but we will go through about them in detail, but majorly we can say that these two are the main parameters concerned. Okay, mean strength is related to the quality and proportioning of the constituents, concrete constituents, and this as we have seen in our mixed design, it is also known as target strength. Okay, and standard deviation is the sigma. Okay, this is a measure of the variation in quality control. Okay, so what this variation is mainly dependent on, so this is mainly dependent of constituent materials quality, proportioning constituents, weight, mixing time, method, mixer, specimen preparation, specimen curing, testing specimen, okay, which are basically dependent of load rate, specimen condition, etc., and basically the age. So all these factors combined will determine the variation. Okay, that is the quality of concrete. Now if we if we see, okay, so this normal distribution, that also again is not a single one. Okay, so different types of concrete, okay, will have different types of standard deviations. Say for example, here if you see, there are two normal distributions. Okay, distribution A, normal distribution A, and normal distribution B. If we observe, we will see that both are having the mean compressive strength to be the same. Okay, but if we see, the variation or the spread of B is much more than that of A. So standard deviation of mix B is greater than A, or A is lesser than B. Okay, but if you see in this case, okay, so here is there is one more normal distribution curve. Let us say it is curve C. So here we will see that the normal the mean strength of A and C are different. That is, yes. Okay, so here we will see that the normal distribution of A, C, and B, if we compare, okay, we will find that the I have shared that. Sorry, is it visible now? Okay, okay, okay. I don't know, something happened, technical glitch maybe. Okay, so if we see here, there are three curves. Okay, three standard normal distribution curves, A, B, and C. Okay, so if we see closely, we will find that C and A, okay, those are having almost similar standard deviation, but the mean strength of C is greater than mean strength of A. Similarly, as we discussed in the earlier slide, if we compare strength normal distribution A and B, both are having same mean strength but different standard deviation. And if we compare B with C, we will find that both are having different mean strength as well as different standard deviation. So that is also independent. It is also like individual concrete samples will have individual normal distribution curves. Okay, so that is the whole criteria. So using this criteria, we try to develop the concept of characteristic strength. Okay, so characteristic, the term suggests, like what it defines is that the designer wants that strength, okay, which is exceeded 95% times the value. Okay, so for that to achieve, okay, we need to design the strength for the mean. Okay, so FCK is the characteristic strength, which is this one. Okay, but if we design for this, we will get like only 50%. Okay, 50% may be greater than or equal, but 50% will be have a chance which is less. Okay, but to get 95% accuracy, like 95% exceedance rate, we need to design for strength which is much more. Okay, so how much more, that will come from the standard deviation into one factor, which is 1.65 in our case. Okay, so we'll find that how it comes. So here if we see, like relating the characteristic strength to target proportioning strength, the characteristic compressive strength is that strength where not more than 5% value fall below that level. Okay, but this is the strength which we are designing for. Okay, that is called as a target proportioning compressive strength. So this is the strength such that characteristic compressive strength is met for a given level of standard deviation. So if, as we discussed just previous slide, so if we design for this strength, okay, 50% will have values greater than that, or and 50% will have lesser than that, but definitely 95% of the values will be greater than this. Okay, so our condition is satisfied. So if 5% of the samples are allowed to fall below the characteristic, and the actual strength of a mix is assumed to be normal distributed, then this is the criteria we get. That is, mean strength is equal to characteristic strength plus 1.65 sigma. Okay, so this concept comes from the normal distribution. Okay, so the mix is designed with a target strength, mean target strength in mind, and not directly the characteristic strength, because we need 95% of the time the value should be greater than the characteristic. So we have to design for the mean strength, okay, not the characteristic strength. So if we want to plot a relation between strength and water cement ratio, it will be always inversely proportional. Okay, that we can also get from the Abrams law we discussed in last class. So it is always inversely proportional. Like higher will be the water cement ratio, lesser will be the strength. Okay, this also we can assume it to be a linear line. Okay, we can assume it to be linearly varying. Okay, linearly inversely proportional, and that slope will be dependent on the variation. Okay, like variation on properties of cement, aggregate, age, etc., etc. So tests need to be carried out to obtain this data, and the strength considered is the real strength. Okay, that is the target strength, not the characteristic strength. Okay, so that is what it has been said here. So each point on this line represents the average of the normal distribution. That is, this strength is basically the target mean strength, not the characteristic strength. Okay, and that is obtained from the normal distribution. And for given material and properties, the variation may be taken to be a single line. Although it is not a single, like it is not a straight line, but it may be assumed to be a straight line. Okay. Now, if we consider concrete more deeply, okay, if we go into more deeply, we can represent the concrete into mainly these 5 phases. Okay, so 4 phases, though we always know, like it is water, cement, sand, and gravel, and the fifth phase, which is the void. Okay, so it is filled with air. So air is the fifth phase. Okay, So here it is a representative sketch. If you see, the gravel is being represented by the bigger circles, the sand is represented by a smaller circle, and the cement and water, it is represented very like very small circles, and the other gray portions we can say it to be the air. Okay, so this is a uniform distribution. Okay, but in the sketch, if we see, this is a lump distribution, like lump representation. Okay, so it is a representation of lump volume basically, and this model. Okay, so here if we see, we have categorized this into 5 parts: air, water, cement, sand, and gravel. Okay, gravel is basically the coarse aggregate. So now if we go into the aggregate part, we will see like there we can like we saw before, we can segregate it into 2 parts. Okay, fine aggregate and coarse aggregate. So from this sketch only, we define this term, which is called the S by A. Okay, so S by A is basically the ratio between sand and total aggregate, that is sand plus coarse aggregate. Okay, so S determines the sand content and A determines the total, that is sand plus coarse aggregate, and this ratio is in terms of volume. Okay, unlike water cement ratio, which is in terms of mass. Okay, so that is the basic difference between S by A and W by C. And the name, besides the name, it is in terms of volume, and W by C is in terms of mass. Okay, so if the value of S by A is very low, okay, if the value of S by A is very low, that means the fine aggregate, that is the sand, is not present. Okay, and that type of concrete is called as no fines concrete. Okay, so there is no sand, and virtually all the volume is occupied by coarse aggregate. Okay, on the other hand, if the S by A value is very high, okay, that means there is no coarse aggregate, almost no coarse aggregate, and the sand content is very high. Okay, so that there is virtually only sand and no coarse aggregate, and that is possible in only in the case of mortar. Okay, so mortar is a type where there is no coarse aggregate and only fine aggregate, so S by A value will be very high. So if we compare all these three, this can be seen here. So S by A represents the volume sharing within the inner materials in concrete, and this helps us to define between a normal concrete, no fines concrete, and a mortar. Okay, so for a normal concrete, the value will be between like in intermediate region from 0 to 1. In no fines concrete, the value will be closer to 0, and in fine this one in mortar, the value will be very high, close to 1. Okay, so clearly the parameter S by A can be used to control the volume of sand and concrete mix. So effectively what it means is controlling the volumetric amount of mortar. Okay, because sand is basically present in mortar, so we can consider everything to be same. Okay, like together. And the question is, should the air content be considered a part of the mortar? Okay, so that is one of the questions which will go we will discuss later. So the the question, the thing is, air is present everywhere. Okay, so air is present in mortar, air is present in the ITZ section, air is present also within the gravel itself. Okay, but the size varies. Okay, so we will see all this in the coming slides. So this marks the end of the first lecture today of the second week. So let us go to the second lecture now. So in this, if you see, this is one of the stories which I'm sure we have been like taught by our grandparents. So there was a thirsty crow, okay, who was feeling thirsty. So he saw one pot, okay, which was having water, but the water quantity was very less and it was down. Okay, so she was not able to drink the water directly. So what she did was she threw stones one by one, and that made the water to rise up, and finally it reached her. She was able to use her beak and drink the water and fly. Okay, so this story represents basically, it can signify the criteria which we require for concrete proportioning. Okay, so that is about the filler and the pitcher material. Okay, so the pitcher we need to fill. Okay, fill by various sub particles. Okay, so if we say like the cement and the water, okay, it is acting as a hydration, the hydrating binding agent. So the other constituents which will be filling, that is the aggregates, as we discussed, the sand and the coarse aggregate. Okay, So we need to fill as much as possible so that the porosity and the void is as minimum as possible. Okay. So the properties of the concrete should satisfy those required conditions and ensure that the pitcher, or in our case the concrete, is completely filled. Okay. And for our case we will always work in 1 cubic meter. Okay. So 1 cubic meter is equivalent to 1000 liters, and based on 1000 liters only we will determine the quantities in concrete. Okay. So now, yeah. So now our job is to find out how much of each of these constituent materials we require. Okay, the quantity should be in kg per meter cube. Okay, and we will calculate the weight of every constituent apart from air. Okay, air basically because the weight of air is negligible. However, the volume in volume case we have to consider the volume of air as well. Okay, we will see it how it is calculated. So fundamental basis, based on like what we have learned in some of the previous slides, like basically what we have to consider is like what concrete is mainly dependent on is basically the slump and the strength. Okay, the governing criteria of slump is basically the unit water content, and the governing criteria of strength is basically the water cement ratio. Okay, so these two are the main parameters based on which every design is dependent. Okay, so let us now see this example. Okay, so here they have given some three trial mixes. Okay, where the W and C is in kg. Okay, the weight per everything is designed per meter cube. Okay, as we just saw. So the W and C, water and cement, is given in kg. W by C is the ratio in percentage. Strength is given in megapascal, and slump, as we know, is given in millimeter. Okay, so here if we see strength in mixes 1 and 3, they are having the same value. Okay, and that is because the W by C is having same value. That because as we just studied in this previous case, strength is dependent in water cement ratio. So if the strength is same, the water cement ratio is same. Similarly, if you see in the second case, like second and third case, the W is same. Okay, if you see the W is same, therefore the slump is same, because slump is dependent on water content. So that has been explained here. So now, as we discussed earlier, okay, so balance between the amounts of fine aggregate and coarse aggregate is required for good concrete, which is dependent on S by A, and it varies with the shape and size of coarse aggregate, fineness modulus of fine aggregate, cement amount in the mix, etc. So the slump basically depends on the aggregate properties. Okay, rounded. If you remember, the rounded aggregates had the maximum workability. Okay, so that means the maximum slump. Okay, and similarly compressive strength mainly dependent on cement, because more is the binding, okay, more is the bond strength, higher will be the compressive strength. Okay, so as much good binding it is able to make, higher will be the compressive strength, and that will depend on the basically the water cement ratio. So durability requirements are also there in cases. Say for example, water should not exceed 45%. Minimum unit cement content should be 400 kg. So these criteria are basically given in IS 456. Okay, there is one table. If I remember, it is table 5. So there it is given what is the criteria for different environmental conditions. Okay. So basically we require these 6 inputs for designing. Okay, one is the air content, second is the slump, and the unit water content relationship, third is the compressive strength water cement ratio relationship, fourth is the S by A. Okay, so if we like if you have gone through the mixed design code, okay, so this S by A was the parameter which was used earlier. Nowadays they use coarse aggregate by total aggregate. But anyhow, both are interrelated. Okay, if you know the coarse aggregate by total aggregate, you can find S by A and vice versa. Okay, so that is the criteria. Fifth is the material property, which is dependent on specific gravity of cement, fine aggregate, and coarse aggregate. Sixth is the other special requirements. Okay, that those are the limitations, maximum, minimum. Okay, so all those give the basically the inputs which are required for designing the mix. Okay, so let us go through now. So first, as we saw, is the air content. Okay, so as mentioned earlier, the air content is in fresh concrete is an input and assumed to be available. Okay, so we it is dependent mainly on the coarse aggregate. If you see the 10262 code, so based on that we assume the air content. Okay, So, or otherwise we can also through trial batches, the dosage of the air entraining admixture we can design, okay, so that we have the exact amount of air, air entrainment or air, the pores which we want the concrete to have, okay. So that was the first case. Second is the water content, okay. So water content is required for the workability or the slump, okay. So as we saw, slump is directly proportional to water content, and it is unit water content, it is linear. So the slope, as we discussed, depends mainly on the aggregate properties, okay. So required slump from considerations such as details of structure and other parameters, and we need to determine the unit water content based on the slump unit water content relationship. So again, if you see the IS 10262, you will find that the this one, the value of water content is given for 50 slump, okay, and it has to be increased for every 25 slump with a rate of 3%, okay. And similarly, if the slump is less than 50, for every 25 it has to be reduced by minus 3%. So like based on this criteria only, those rules have been formulated, okay. So we have discussed about air and water, okay. Next I think will come the cement, okay. So cement content, so that will basically that is mainly calculated from the strength and water cement ratio, okay. So strength is the target mean strength which we just discussed, okay, and the water cement ratio, that will we will find out from the compressive strength water cement ratio relationship, okay. So based on that strength and the grade, okay, we find the water cement ratio, and once we get the water cement ratio and the water content, like previously we calculated, from that basis we get the cement content, okay. So required target strength is calculated, then we determine the required water cement ratio based on the strength water relationship, WC relationship, and from the water content we find the cement content, okay. Now after we have calculated air, water, cement, the two other parameters which are remaining are the content of coarse aggregate and fine aggregate, okay. So before that, one more thing, this the durability factor, okay. So durability factor will be dependent on some other conditions as well as heat of hydration. So those factors comes in the other part, okay. So we will see later how it affects the concrete proportioning, okay. So now let us go to the fine and coarse aggregate content. So the remaining volume basically will be fine and coarse aggregate, okay. The problem is like what we have calculated till now, water, cement, so those are mainly in weight, okay. So because air is not present in weight, okay, so we need to find everything in volume, okay. So therefore using specific gravities we have to convert, air is definitely in volume, we have to convert water and cement in volume, okay. From that we find this, okay. So we find basically the amount of volume present and the S by value, okay. So using both we find the volume of fine aggregate and coarse aggregate, and again using specific gravity we find the weights of every constituent, okay. So using that relationship we basically find out the air, water, cement, fine aggregate, coarse aggregate for 1 meter cube of concrete or 1000 liter of concrete, okay. So if we fine tune even further, we will get the 5 basic steps in normal concrete proportioning, that is air content, water content for required workability, cement content, sand content, and coarse aggregate content, okay. So step by step we can find out every parameter required for the mix. So now let us in a nutshell review what are the rules, okay, for the mixed proportion. So that is basically start with the target slump, air content, and compressive strength, and then carry forward the other parameters, okay. So once the air content is known, the unit water content is found out, then the water cement ratio, sand aggregate ratio, and using the specific gravities we convert from volume to weight as well as weight to volume, okay. So obtained results could always be different, so because of the site conditions, and that's why the minor adjustments are to be made in the proportions which we shall see now. So in the discussion so far we went through the procedure for proportioning a concrete mix, which is normal, okay. and learn what kind of information or input data is required to be able to carry out the exercise. So now we are ready to work with some live practical examples and try to see how the process actually is a design mix. Okay, so let us take this example. For example, this say for example this we need a concrete mix which is having air content to be 5%, slump is 80 mm, characteristic strength is 25 megapascal, standard deviation is 3 megapascal, as by value is 0.36 or 36% by volume, and these are the specific gravities. Okay, so based on the data given, okay, and from the slump unit water content relationship, if you see, like we can calculate based on slump of 80 mm, we can calculate the W to be 160 kg per meter cube based on certain criteria. Okay, so those criteria are basically available in IS 10262. Okay, so based on that, after that we try to find out the target strength, which is equal to FCK plus 1.65 sigma, as we just discussed. So it is 25 plus 1.65 into 3, which is 29.95 or 30 megapascal. And then after, from the strength WC water cement relationship, we find the water cement ratio, which is coming to be around 50%. Okay, so based on that, if you see, because the water cement ratio is 50%, so the water is 160, as you can see. So there definitely the cement will be 320. Then only W by C will be 0.5, and air is given 5%. So 5% into this one 1000, it will give 50. Okay, 50 liters. So that is 50, and then FA is 645, CA is 1178. Okay, so this has been calculated based on this volume. Okay, so basically water and cement, these are found in weight, then they have been converted into volume, and then this is 50. Okay, so they have minus 1000 minus 50 minus 160 minus 103.2. This gives the total. Okay, and based on S by A value, which is 36.36. Okay, so they have calculated the FA and then again deducted that to get this one. Okay, and after they have calculated the complete volume, they have again shifted it to back here to find both in volume as well as weight. Okay, so that is what has been explained here. Okay, so they have calculated the fine and coarse aggregate volume by subtracting, and then using S by relationship, they have calculated the volume of fine aggregate, coarse aggregate, and then again they have using specific gravity found out the weights. Okay, so with this, this lecture has been completed, and we have basically got the idea as to how to the main steps. Okay, that are required for getting the concrete mix. Okay, basically we need the slump water cement ratio. Okay, and the target strength. Okay, so based on that we can find out almost everything, and based on the S by I value we can find out the volume. Okay, so now in the next lecture, let us find out what happens if some minor adjustments are required. Okay, so till now we have gone through the numerical example and tried to develop a single algorithm based on some experiments and properties of materials, and try to find out that the steps required for getting the desired properties of concrete. Okay, so that it can be implemented for determining the concrete mix proportions. So some analysis of the proportions we obtained in the last class, that is the last lecture, and we need to adjust. Say for example, some site conditions say that our some of the properties are not matching our theoretical paper value. Okay, so how to adjust or revise the proportion so that the actual design is satisfied. Okay, so we will go through this now, and also we will see like how using some admixtures, that is chemical and mineral admixtures, using that how we can further modify and blend the properties. Okay, so in the last problem, if you remember, we had taken this as the values. Okay, air entrainment was 5%, water content was around 160 kg, water cement ratio was around 0.5, and S by A was 0.36 by weight by volume. Okay, so this was the condition. Okay, so if you see here, you will see, we will find that cement, okay, in it constituted around 10% volume of the concrete and 14% mass. Okay, Space, on the other hand, it consisted of 26% by volume and 21% mass. Mortar, it was almost half, okay, 56-49, okay. In mortar, they have considered the air as well. On the other hand, the coarse aggregate, it considered around 44-50, okay, and the inert materials they considered around 70 to 80%, okay. So basically, the coarse aggregate had contained majority of the portion, around 50%. The cement, the sand, that was around 25 to 30, and the cement was around 10 to 15, and the water around 10%, and the total mortar it consisted 50, okay. So that is the volume distribution of the concrete materials, okay. So now, say for example, why we need the minor adjustment, okay. So that can be, arise, okay. It can arise if the concrete does not have the properties we assumed or targeted, because in site conditions many unknown things happen, okay. So that may result in unwanted things may happen, which may result in requirement of minor adjustments, okay. Or if the properties of the materials used have been changed, okay, because some unwanted or uncertain situations, okay. Say for example, the finest modulus of the sand has changed, or there is a change in the properties of cement or chemical admixture. So we have to take into account all these conditions so that we are foolproof, okay. So these are the basically criteria, okay. So these are the corrections which can be done in S by and W, okay. The water content and sand by total aggregate content. So these are the corrections for change in fineness modulus, slump, air content, and water cement, and S by, okay. So these conditions for minor adjustments, they have been taken from SP2 1986, okay. So sorry. So in this example, okay, say let us consider that we have there is minor adjustment in slump and minor changes in slump and air content, okay. Say for example, there has been 1 centimeter increase, okay. We need like 1 centimeter of slump has decreased, and air content has also decreased by 1%, okay. So we need to increase the slump by 1 centimeter and the air content by 1%, okay. So for that, what to do, okay. So for that, we need to consider this, okay. So basically for slump, we don't have to change anything in S by A, but we need to increase the W content by 1.2%. And for air content, we have to change, we have to reduce S by A from 0.5 to 1% and reduce W by -3%. So as you can see here, so as I told you, say like we wanted 80 mm slump, but we had 70, okay. And we wanted 5% air content, but we have actually 4%. So how to increase that 1%, as we discussed just now? So we need to increase the change the S by A and W values based on those recommendations, okay. So based on after adding both recommendation, we get the net change in S by A value to be -1% and W to be -1.8%, okay. So the W value which we calculated was 160, okay. So if we have to reduce 1.8%, so 1.8 of 160 is 2.9, okay. So if we reduce 160 minus 2.9, we get 157.1 or 157, okay. Similarly, we have to reduce S by A percent by -1, so it was 36, we reduced by 1, it became 35, okay. So now one factor we have to consider here is that although we have changed W, okay, but we don't have to change W by C. But if we are subtracting W value, so definitely the W by C value will also change, okay. So to keep in mind, to to make the W by C value constant, okay, so we have to reduce the C value, okay. So that's what this we have to keep in mind during this whole calculation, okay, because the W by C value has to be constant, as nothing has been mentioned here. So if you see here, so basic case, in this case, if you remember in the calculation, we got 160 and 320 as the water cement content, and the other values were as such. But in this case, because we have subtracted 157, okay, so we have to again minus 314, like we have to minus 320 minus this -6 has to be done, so that the W by C value is again 0.5, okay. 157 by 314 is 0.5. If we have considered 320, it would have been less than 0.5. So no, we have to consider that and make it constant, okay. So now Using these recommendations, we find that the slump and the air content will be satisfied. Okay, and then there is uncertainty. There may be some uncertainty also about the properties obtained in the trial runs. Okay, which are replicated in the field. So the best way to handle all those situations is to make the criteria, like theoretical criteria, as much stringent as possible during trial mixes. Okay, say for example, if we consider that the criteria to be 8 plus minus 1. Okay, the error, if we can minimize to 1%, so in the site condition we can increase to 2. Okay, similarly, if the error percent, if we can confine it to 0.5, the variation, we can increase it to 1. Okay, but if the trial value is only having the range, the error range higher, so final range will be even higher. Okay, so that's why it is important that to reduce the uncertainty as much as possible, the criteria made should be as stringent as possible. Okay, and the record should be kept for every successful as well as unsuccessful mix. Okay, because those help in future mixes. Okay, so based on this, let us go through one more example. This time we will use admixtures. Okay? So the question is why we need to add admixtures. We will see now. Okay, in the coming slides. So in this example, let us consider that we need to prepare a normal concrete and proportion it based on these conditions. So here air content is 5%, you need water content 180, water cement ratio 45, Ca content 40. Okay, and the cement content should not exceed 320. Okay, so let us assume that we have two admixtures. Okay, one is a water reducer, which is basically a chemical admixture, which can reduce the water demand by 20%, and second is the mineral admixture. Okay, which has an efficiency of 75%. Okay, so we need to carry out the proportioning exercise for meeting the above mentioned conditions. Okay, so this is basically the design. Okay, normal design. Okay, so they have calculated the values, and they have using by calculating the volume as by values, they have again found the fine aggregate, coarse aggregate, and all the other constituents. Okay, so that is the normal concrete design. But if you see here, it has been mentioned that 320 kg should not be exceeded. Okay, so here if you see, we have got the cement value as 400, so it has exceeded that. Okay, so therefore it can be utilized. Okay, so here comes the use of mineral admixture. Okay, when we want to reduce water or cement value, so there, or water by cement value, then we use the concept of using admixtures. Okay, so how does that work, we will find out here in the coming slides. So the mixed design does not meet the other criteria, as I just mentioned, as the cement content exceeds the maximum permissible value. So the cement content can be brought down in two ways. Okay, one is by reducing the water content. Okay, so because we have to reduce the water, so in order to keep the W by C level value constant, we have to again reduce the cement. Okay, so by this way the cement content is reduced below the permissible value. Okay, maximum permissible value. So that is the concept of chemical admixture. In the also we can also utilize the concept of mineral admixture, where they replace the cement partially. Okay, directly replace it partially with respect to its efficiency. Okay, so by that logic also we can bring the this one, the 400 kg cement to less than 320 or equal to 320. Okay, so this in this mineral admixture case, it mainly depends on the efficiency of the admixture. Okay, so both using chemical admixture and mineral admixture, we can bring the cement content down to the desired levels. Okay, so first case. Okay, let us use the chemical admixture case. Okay, so in the chemical admixture, what we can see is, since the maximum unit content is 320 and the WC has to be kept at 45. Okay, so the unit water content cannot be allowed to exceed 1/4. So in order to keep the cement content as 320, okay, and to keep the W by C as 45%, so if we calculate, then W by 320 equal to 0.45 will come, the W value will come around 144. Okay, so it can exceed 144. Okay, so in other words, we have to use a chemical admixture which sorry, which reduces the requirement of water from 180 to 144, that is 36 or around 20%. Okay, So this so we need to find a suitable chemical admixture which is capable for a particular dosage. It is capable of reducing the quantity of water required from 180 to 144. Okay, so if we if we use that appropriate dose of suitable chemical admixture, okay, so we will get the required value. Okay, so using that, if we see that air, water, water and cement, water value they have brought to 144. Cement has because they have been able to bring the water value to 144, the cement has come to 320, and 0.45 water cement has been maintained, and this has been able to satisfy the maximum the permissible it has been able to bring down the cement into the permissible content. Okay, so so this is satisfying the whole problem criteria. Okay, so that is the first case, okay, by using chemical admixtures. Okay, secondly, we can use the mineral admixture case. Okay, so in that case we just directly need to replace the cement partially. Okay, so by partial it means that we have to remove the excess content than the maximum permissible. Okay, so maximum permissible was 320 and we needed 400. That means the excess required was 80. Okay, so 80 kg, if we can replace cement with the admixture, so our problem gets satisfied. Okay, our problems get solved. Okay, so if the mineral admixture is having a 75% efficiency of cement binder, so that means like we have to add more. Okay, to how much more than 80? It is found by dividing the 80 by the efficiency. So dividing 80 by 0.75, we get around 106.7 kg. So this much amount of this one, the mineral admixture, which is having 75% efficiency, it will be equivalent to 80 kg of cement binder. Okay, so by using this concept of mineral admixture, we can directly replace cement partially and bring down the required bring down the level and satisfy the required conditions. Okay, so using that, we, as you see, the water has not been touched this case. This is 180 itself. The cement has been brought to 320. Okay, so the cement has been brought to 320 and 106.7 has been the mineral admixture, and FA is 569.8, CA is 1052. So in this case, as you can see, water has not been changed, but the water cement ratio is constant. Okay, so you may feel like this is 180 by 320, but this is actually 180 by 320 plus 0.75 into 106.7. Okay, so which is equal to 0.45. So the water cement ratio is maintained. Okay, so that is the benefit of using mineral admixture. So if we compare all the three, we will see this as the sketch. Okay, so in basic case we could design, but the cement was exceeding 320. In the chemical admixture, we were able to bring the water down by using some suitable chemicals in solution, and because of that, the cement was also brought down to the required limit. And in mineral admixture, we use some supplementary cementitious material or the mineral admixture, which we will find later. So those were able to substitute partially the cement in terms of its efficiency, and maintain the water cement as well as the required conditions. Okay, so that is all about using the admixtures and the minor adjustments. Okay, so let us come to the next lecture. Okay, that is in this lecture we will study about the pores and the porosity. Okay, how to measure porosity and what are the pores present inside concrete. So porosity, as we discussed previously, porosity in concrete comprise like they are present mainly in two parts. Okay, one is the porosity that is present inside the aggregates, and second is the porosity which is present in HCP. HCP is nothing but hydrated cement paste. Okay, so as you can see here, the diagram is self-explanatory, and we have discussed in the first class how the pores are marked. Okay, so the pores always the porous channels always go through the side of the aggregates, coarse aggregates, and that's why the ITZ the interfacial transition zone is the weakest zone. Okay, so we have discussed all this in the last class. So the now we will focus on understanding the porosity in hydrated cement paste, and we will use some models and schematic sketches to understand it in good detail. Okay. So if you see in this case, so this is basically the representation of hydrated hydration model of Portland cement. Okay. So before cement hydration, as you can see, these blue circles, small and big, are the cement particles. Okay. So when the hydration occurs, the CHH gel starts forming all around, and if the hydration is complete, so everything will result in formation of gel. Okay. So due to this, the sizes get increased. Okay. And after this happens, we see that this basically this compounds are basically formed. Okay. It has four main complexes which hydrate independently. So the C3s and C2s are basically the string giving. C3a is basically for flash setting, and C4af gives some other parameters, soundness and all. And this C3 C3s basically gives the initial string, then C2s gives the later string. Okay. If you see, these are the heat of hydration. Okay. So the based on this, we use different types of chemical admixtures also, which can accelerate or retard the use of the hydration. Okay. Because in some cases the hydration may be more hydration is required, and in some cases the rate should be slow because of some reasons. Okay. We will discuss those also. So as you can see, these are some stoichiometric relations which are present in hydration of cement. So chemically, if we find the amount of water which is required for hydration, it is between 18 to 22%. Okay. So this much water is sufficient for hydration of cement. Okay. But to achieve this, we give water which is in much more much more in content as compared to the required value. Okay. So water added is always far in excess, and generally it is ranges between 40% to 55. Okay. So you see, we require between 18 to 22, but we are giving 40 to 55. Okay. So this excess water, na, so this excess water, it stays even after complete hydration. A lot of water remains after that. Okay. And that water basically, when it gets evaporated, as we will see in coming slides, as it gets evaporated, the that results in the generation of pores. Okay. So the main reason for generation of pores, apart from compaction, is the water present inside the concrete. Okay. Excess water. So if we see here the volumetrics of cement hydration, before hydration, we can in the binder we can see like water and cement is the main constituent. Okay. So after the formation of after the hydration starts, there is some amount of pores. Okay. This is generally the water. The white color represents the water which is evaporated. Okay. And the water is present because the hydration is going on along with the hydration products formation and cement. Okay. After the complete hydration happens, okay, very little unreacted cement is left, and maximum hydration products is formed. uh, Above that, the water, okay, which is left is there, plus in the white color the water that is evaporated. Okay. So these two, okay, total in total represents the total amount of pores that has been generated. Okay. So let us consider a paste, okay, which is having a W by C of 40%. Okay. So if we consider cement content to be 314 gram, by using this relation, we will get water to be 125.6 gram. Okay. So the specific gravity of cement, if is 3.14, the volumetric composition of the paste is 100 cc of cement and 125.6 cc of water. Okay. So that is total of 225.6 cc and 439.6 gram. Okay. So let us assume that complete hydration, you know although it is 18 to 22% is required, let us assume that 25% water is required for complete hydration. Okay. And also let us assume that there is no change in volume in cement paste during hydration. Okay. So based on that, what we will find is that out of 125.6 gram, okay, 78.5 gram, okay, that is 25% of water cement of the cement content that will be consumed in hydration. Okay. So remaining how much is there? It is 47.1 gram of water. Okay. That will be left behind as unreacted. Okay. And that will eventually escape. Okay. Which is resulting in the void space, as you can see. And the if we assume the initial volume of the paste as 225.6 cc, as we found here, So the assumptions and arithmetic using all those, we will find that the hydration products will weigh around 392.5 gram, because 47.1 gram of water will be left behind as unreacted, okay, and occupy 178.5 cc, because this 47.1 will result in evaporation, okay. So as you can see, apart from the blue water here, the there are some blue small slanting lines also present in the HCP, okay. So these are basically the gel pores, okay. The pores formed in the gel due to the presence of unreacted water, okay, which will also get evaporated, okay. So this is the initial and this is the final diagram. So we will again go into more detail now. So this is the schematic representation of the hydration process at an intermediate stage, where there is some unhydrated cement, as you can see here, and when and some hydrated cement paste, okay, which is having some pore spaces. These are the blue lines. These are representing those pore spaces. So the removal of this water from the concrete over a period of time through evaporation, okay, so that is at the root of the pore formation, okay. So we discussed this water that will get evaporated will result in the formation of pore, okay. And this discussion also clearly established that pore space in concrete will be higher in cases the water cement ratio is higher, okay. This is obvious, because more will be the water present, more will be the more will be the water evaporated, bigger will be the chances of pore spaces, okay. So this again qualitatively validates our basis of W by C, WC versus strength rule, or what we say is the Abrams law, okay. So porosity is also plays a good factor, okay, in the water cement versus strength rule, okay. So here, as you can see, this is the aggregate, this is a cement paste matrix, and here if you see, this space is mainly dependent for the generation of pores and the presence of unreacted water, okay. So more is the water present, more will be the porosity, and more will be the channel, okay, porous medium for ingress of all those unwanted materials, okay, such as chloride ions, which result in corrosion, okay. So if we go more deeper, we will see that if we want, we can divide this sketch into various parameters, such as empty pores, free water, gel water, chemical bound water, hydrated cement, unhydrated cement, aggregate, okay. So the hydrated cement paste basically consists of hydrated cement, chemically bound water, and gel water, as we just discussed. So main pores is coming from the empty pores and free water, because this will also get evaporated, but gel water is also contributing little bit to the porosity, okay. So pores in cement-based materials, okay, such as concrete and mortar, they have a they are porous, okay, and they have a complex internal pore system, as we will see now. The hydrated cement paste mainly they contain the capillary pores, as also the as well as the gel pores, okay. These are smaller in sizes. We will see the sizes also now. And the main pores which we will study are the capillary pores, okay, like which is of our concern, because their size range is very big, okay, and they have a large variation in size due to the cement particle spacing in water cement suspension, okay. So they have a different variation, okay, like big variation. And spherical air voids with diameters larger than 20 microns, naturally or artificially introduced, are also present as air voids. These are basically the empty pores, okay. So, in the neighborhood of aggregates, there is the ITZ, more porous zone is present. Presence of pores is at the root of almost all durability related problems, which result in ingress and movement of deleterious ions or materials like the chloride ion through the pore space, okay. So this makes us to be realize that concrete is not as much solid, okay, as we think it, okay. So in words we always use like we need a concrete solution, but that concrete also has some pores, okay. So pores in concrete, okay. So basically those pores they can be categorized into 5 types, okay. So these are the sizes, okay. So basically entrapped air, entrained air, capillary pore, gel pore, and intracrystallite pore, okay. So let us find out what are the definitions. So entrapped air is air which is entrapped air is basically the pores which are unintentional air in concrete, okay, due to the unintentional presence of air in concrete. Entrained air is the presence of air due to the intentional air which is which is created by use of chemical admixtures. Capillary pores is that pores, as we discussed, which is present in the HCP, cement paste, and the aggregate interfacial zone, and it is the main pore of our concern. Okay, gel pore is present in the gel. Okay, as the name suggests, it is a result of hydration products. And intracrystalline pores are also present, which are very much smaller as compared to gel also, and they are also present inside gel. So if you see the sizes of entrapped air, it is always greater than 1 mm. Okay, greater than equal to 1 mm. Entrained air lies in the range of 10 micrometer to 250 micrometer. Okay, so it is less than 1 mm, and it is between 10 to 250 micrometer. Capillary pore, on the other hand, it varies from 3 nanometer to 30 micrometer. Okay, so it is a very big range. Okay, so that's why these pores are of very much concern mainly. So apart from that, there are other pores such as gel pores, which is having 1 to 3 nanometer. Okay, and intracrystalline pores, which is less than equal to 1.2 nanometer. So these two pores are of not that much important, but we should know because all these pores are present inside concrete. Okay, so basically, as we discussed, the capillary pores are the most important pores, which is having a range between 3 nanometer to 30 micrometer. Okay, so it is a very big range, and it is succeeded by entrained and entrapped air, and preceded by gel pores. Okay, so in most concrete spaces, it is occupied by capillary pore, and therefore it is important to clarify the property of capillary pores. Okay, so now let us go through how to characterize the pores. Okay, and find how to analyze the pore size. Okay, so let us take this illustrative example. Okay, let us take a pore structure as shown here. Model pores, which are cylindrical, they are having associated diameter and volume. So concrete, they should have pores of varying diameter and size. Okay, so let us assume that there is a pore structure A. Okay, which is having three types of pores. Okay, having D1, D2, D3 diameter, and names are and lengths of L1, L2, L3, and number N1, N2, N3, volume V1, V2, V3. Okay, this type. Okay, and similarly, let us take one more pore structure B, which is little different. Okay, as you can see here. Okay, so if we compare both, we will find that the total pore volume in both the cases will be V1 plus V2 V1 plus V2 plus V3. Okay, however, in pore structure A, what we will see is that the largest size pores, that is D3, is having the largest volume, which is not true in B, because in B the largest volume is occupied by the medium size, that is D2, not D3. Similarly, in A, the small size pores occupy the least volume, that is D1 is having the least volume V1. However, in B, the largest pore, okay, large pores occupy the least volume. Okay, so D3 is having the least. Okay, so here the small size occupies the least volume. Here the large pores occupy the least volume. So both are not equal. Okay, so that is the difference. Like how to characterize, we need to find out. Okay, so if we characterize, we will find the properties are different for various types of concrete. Okay, so basically there are two parameters to evaluate the pore structure. Okay, one is the total pore volume, or TPV. Okay, and the second is the distribution of pore size distribution, and that is called PSD, or even differential pore volume. Okay, DPV. Okay, so here mainly comes the concept of, we should also include this concept in our discussion, which is basically the pore connectivity in concrete. Okay, this is central for understanding any porous material, and this connectivity basically facilitates the movement of material within the porous material. Okay, so if we have if you remember, in the last class we said, we had discussed that the red lines are those lines which are connected entirely, okay, like throughout, okay, throughout the pores, throughout the concrete. However, these blue lines, okay, these are present in the intermediate ranges only. Okay, so they don't facilitate transfer of chloride ions all throughout the concrete, but the red lines, okay, they generally are interconnected everywhere. So chances of chloride attack or corrosion is much more higher in the red lines. Okay, but the blue lines, they are of not that much important, like not that much dangerous, because they are not connected throughout. Okay, so this facilitates the movement of material within the porous material. Okay, so connectivity of pores is, that's why, important. So porosity, basically it is a measure of the void spaces in the material and it is a fraction of the volume of voids, which is called VV, over the total volume, okay, VT. That is VV by VT, and it can be defined in cc per cc or cc per gram, okay, and it can be expressed as ratio between 0 to 1 or percentage between 0 to 100%, which is same in most of the ratios, okay. So porosimetry basically it is the measurements, okay. Porosimetry is basically the measurements of pore size, volume, distribution, density, and other porosity related characteristics. So basically we are concerned about size, volume, and distribution, okay, and from there also we can determine the density, okay. So these are the porosimetry measurements which we are interested, okay. So say for example, if we consider a pore system with diameters ranging from D1 to D4, okay. So here we will see that say for example in this schematic representation, so there is a solid which is having pores of D1, D2, D3, D4, such that D1 is greater than D2, greater than D3, greater than D4, and they are having lengths of L1, L2, L3, L4 respectively, okay. So here if we see the multiplying the this one, the diameter with the this one, the length, we will get the volume, okay, volume fraction of the different sizes, and the total area represents the total volume of pore space, okay. So that is like if we in some if we consider, like in some ideal case, if we consider this way, we can calculate the volume, okay. So for that, okay, for that we use an experiment or a test which is called as MIP. The full form of that is mercury intrusion porosimetry, okay. So in this case we intrude mercury into the pores, okay, in the experiment, and try to find out the volume as well as the size based on the intrusion, okay, the amount of mercury that has been that has gone into the pores, okay. The reason we use mercury and not water is because mercury is a non-wetting liquid, okay, unlike water, which is a wetting liquid, that is it reacts with the substance, okay. So that will not result, that will not give us, and like it will not give us an exact measurement of accurate measurement, and it will be giving some varying measurements because of the wetting nature, okay. So that's why mercury is basically used in this experiment. So if we consider, like we have inserted we have given p pressure of p in mercury, and this pressure, this liquid has been inserted here, okay, into the pores, which is having a diameter of d, okay. So we will find, like based on principle of compatibility, we will find it, this the force that is given by the mercury is p into pi d square by 4, okay. So that is like that has been reacted by the surface tension of mercury, okay. So which is nothing but g cos theta or cos q. Q is the contact angle into pi d. Pi d is the basically the perimeter, okay. So if we see this using this relation, we can find out the d, that is the size of the pore, based on the variation of pressure, okay, that is p. So this relation d is equal to 4 g cos q by p, that is the relation using which we can find out the pore size, okay. And based on this, you can see only that d is inversely proportional to p. That means when the pore diameter is small, the pressure is very high, okay. The high pressure is required to enter small pores, okay. Similarly, if the d is big, p is small, that means less pressure is required for entering a pore of small size, okay. So using this, we can find out the pore size, okay. And if we calculate the volume of mercury intruded, okay, so using how much volume has passed through, we will be able to find out the volume of the pores, okay. So using both criteria, we can find the size as well as the volume, okay. And normally the sample size is generally less than 1 by 1 by 1 centimeter, okay. So we have to use some specimen parts, okay, of the concrete to find out the porosity, okay. And this is the apparatus where the cell is filled with mercury, and mercury pressure is applied from top, okay. So it measures both pressure and volume of mercury intruded in the sample and obtain the pore volume within the sample, okay. So the pressure gives the diameter, that is the pore size, and volume gives the pore volume, okay. So how is it calculated, okay. So say for example at an instant t1, P1 was applied, okay, P1 pressure was applied, and that meant pore size of D1, okay. And after some time, if we increase the size from the pressure from P1 to P2, okay, so we get the size as D2, okay. So based on the volume intruded, we get the pore volume, and taking the average of D1 and D2, we get the average diameter D1 prime, which is the pore size, okay. So therefore pore size is the average of the initial pore plus the size of the later pore, okay. So the average of both the pores gives the pore size, okay, for the particular volume V, okay. So by this we calculate the cumulative pore volume, okay. And as you can see, as the pore diameter reduces, the pore cumulative pore volume increases, because as the diameter increases, the force as the diameter decreases, the force increases. So more is the increase in this one, the mercury pressure, more is the cumulative pore volume, okay. So that is the relation all about. So therefore we can say that mercury porosimetry is based on causing mercury to fill the voids in sample by pressure application. The pressure required increases the diameter of pores as the pressure increases, the pressure increases as the pore diameter decreases. So it is easier to fill pores of large diameters, because as we can see from the relation, and measuring the pore volume of mercury intruded gives the pore volume corresponding to that diameter, as we just saw, okay. So operationally, the measurement works as follows. We firstly create a vacuum in the pore system. We push the mercury in steps, increase the pressure gradually, okay, with a pressure timetable, and note the amounts of mercury intruding into the pore system at differential pressure levels, okay. So analogous to how we do a compression, so this whole process is similar to what we do in compression or tension test, okay, in CTM or tensile testing, okay. So in that case, what we see is as the load increases, okay, the deformation gets increased, okay. Similar is the case in mercury intrusion porosimetry. What happens is as the mercury pressure increases, okay, the pore volume also gets increased, okay. So amount of intrusion occurs increases, occurring increases, and that's how we get the pore volume and also the size. And more is the pressure, lesser is the size, okay. So as the pressure is increased from a lower to higher level, the pores are filled in a sequence from larger diameter to smaller diameter, okay. But this is the one of the problems associated with mercury intrusion, okay. So that it has to be filled in from a sequence of large diameter to smaller diameter. It can be random, okay. So we will see how, like, why this is a problem of the testing of MIP, okay. So so that is the case. As we saw, for particular sizes we have particular pressures have been assigned. So the smaller is the size, the greater is the pressure, okay. So based on this we get the pore volume and the pore sizes, okay. So now let us see the problem, okay. So everything works fine when the outer pores are larger in size than the inner pores, okay. So if the pores are like this, okay, gradually decreasing, okay, so then we will get the exact the mercury from MIP test, we will get the exact pore distribution and pore size and pore volume, okay. However, if this is the case, which is actual case in real situation, this is the case, so then becomes the problem, okay. So here if you see D2, okay, D2, based on D2 we get P2, okay. P2 gives the pore size of D2, okay. So after that, because this is small, okay, so we will exert a we will give a higher pressure. So higher pressure will result in intrusion of mercury here, okay. But because this is because this size is higher, bigger than that, okay, so here less pressure is required, okay. So since we are giving more pressure, okay, so therefore the intrusion will not stop here, it will go up till here, okay, till the size is lesser than the that size, okay. So because of this only we have filled entire this, okay. So we expected D3 but we got total, we wanted this one but we got total. Similar is the case here, okay. So here the size is small, so pressure is high. Here the size is high, so pressure is less required, okay. But because pressure is high, so everything gets intruded. So we wanted D4, we got D1 plus D4. So what this results is, this results in an overestimation, okay. So overestimation of small pore size is the deficiency of MIP. So I hope you got like you understood what is this problem. So that is one of the anomalies associated with this test, and this is also known as the ink bottle effect. Okay, so that is the effect as this is the problem associated with mercury intrusion porosymmetry because of its mechanism. Okay, so as you can see, this is how the pieces of samples are collected, and these are the cells from measurement. Okay, and here you can see that this is a porosimeter where we have to fix the cells and perform this experiment. Okay, so based on this we get this type of curves. Okay, so the pore this is the cumulative intrusion volume ml by ml by equivalent pore diameter in micrometer. So as you can see here, the pore volume curve of 7 days is higher than 210 days, probably because of the hydration. Okay, so more it is the hydration, the pores got filled. Okay, because of the water, okay, which reacted. Okay, but it was not able to eliminate the entire spaces. Okay, so that resulted in pore spaces left leaving behind. Okay, so they were left behind. So similarly you can see here also in the log differential intrusion, similar things have been shown. Okay, now if you see, this gives us the pore size distribution. Okay, so based on this we can also find out some new parameters like we can find out the median pore diameter, or we can find that the size d10. Okay, d10, say for example, is the size which through which only 10% only 10% of pores can pass. Okay, so out of the total pore volume, say for example only 10% is able to pass, so that is the size of the this one d10. So like this we can find out various new terms, coin new terms, and find out we can give some we can show some representation. Okay, so we can find out some details about the characteristics of the pores. Okay, so that concludes that lecture, and let us come to the last lecture. Okay, so for this week, so that is based on admixture. So what we learned in chemical what we learned just a few lessons back was about the chemical and mineral admixture basically. So here we will go through them in little bit more detail. Okay, so what are its applications, why it is used, why is it necessary, and how it can be improvised. Okay, so what is admixtures in concrete? So in addition to normal constituents, that is water, cement, sand, and coarse aggregate, other additives added to concrete, okay, they are known as admixtures. So they are added for various reasons. It may be technical, as we just studied. Okay, those were mainly technical reasons. Otherwise it can be economical and environmental concerns also. Okay, so using all, because of these three factors, we basically use admixtures. Okay, so we will discuss the admixture from an engineering point of view. Okay, and we will stick to like the basics only. We will not go into chemistry because it is beyond the scope of this course. Okay, so admixtures, as we just studied, they are basically chemical and mineral admixtures. Okay, basically. So chemical, as we all know, that mainly reduces the water content, and mineral admixture is mainly associated with partial replacement of cement. Okay, there are other materials also which can be used in concrete. So they are basically, say, for example, recycled aggregate, slag, copper slag fibers, etc. So the difference between admixtures and those are this: admixtures are basically they are influencing the binding the hydrated the reactive components. Okay, that is the water and cement. The other materials are basically used as a replacement of the filler, the non-reactive components, that is the aggregate, fine and coarse. Okay, so there they can replace sand, coarse aggregate, and this is useful because they serve both the purpose. Okay, the utilization of waste material and also the preservation of natural resource. Okay, so now let us go into a little bit more detail. What is chemical admixture? Okay? Chemical admixture, they interfere with the action of cement within concrete, which can include the hydration also. And depending on the need, they can be chosen. Various types of chemical admixtures are available. So basically, which we used, in the previous example was that of the water reducer. Okay, so if it is a simple water reducer, it is a plasticizer. If it is a high range water reducer, it is a super plasticizer. And they can also be used as some, increasing and decreasing the rate of hydration. So that is known as regulators. So it can be both accelerator as well as retarder. Okay, so as we saw this sketch, okay, so these are the cement particles. So after hydration, these products get formed encircling the circle, okay, during hydration. So chemical admixtures, they are usually available as liquids. Okay, and often mixed in volume. So the dosage is very small. That's why at the time of mixing, various special care should be taken. And the pure mixture is generally admixture is mainly often diluted with water, okay, and added as a part of the unit water content to required to be mixed, so that better distribution is there, okay, dilution and distribution. Otherwise it may get concentrated at only some regions in concrete. So the dosage of chemical admixtures is therefore very less concentration is mixed, okay. So like for example, it is generally less than 4%, okay. So here say for example, we have taken a dose of 1%, okay. So 1% by weight of cement in a concrete containing say 400 kg per meter cube of cement, so that will come up to 1% of 400 will come around 4 kg, okay. So 4 kg of admixture per cubic meter of concrete will be used if the dosage is 1%. So if the if we consider the unit weight per cubic meter of concrete as 2400, okay. So if we see 4 kg and compare 2400 kg, so we will we will find that 4 kg is even lesser than 0.2% of the weight of concrete, that is 2400, okay. So see, so that this is the concentration, okay. It is very less, 0.2%, okay, even lesser than 0.2%. So the chemical admixture, it can be available as an aqueous solution, okay. So say for example, if we want to dissolve 4 kg in 10 liters, okay, or say for example we want to this is 1%, okay, or if we want to dissolve 1.5%, that is 6 kg in 15 liters, okay. So this 10 and 15 liters, okay, they can either be adjusted, okay, or they can be added, okay. So that is based on our this one our choice, because anyhow this 10 and 15 liter is not going to affect the amount of this one the proportion, okay, because they are very high, okay. This is negligible almost, because the amount of water that is needed is very high as compared to 10 and 15. So this can be we can use it both ways, okay. So let us come to what is the role of accelerator or retarder, okay. So they are used under mainly special conditions, okay. So when concrete is used in cold or hot temperatures, so then there is the need to regulate the setting process, okay. We need to either accelerate it or retard. Even it these regulators are used for mass concreting purposes, because as we all know, the process of hydration is an exothermic process. So if lot of casting occurs, okay, the heat generated will be liberated will be very high, and that will result in unhuman conditions of working, and also it may result in honeycombing and cracks formation. So that's why both of these are used to make it more so that the design is more achievable, and there is no unnecessary problems generated, okay. So retarder could be used to prevent formation of coal joint. Coal joint is basically the separation of concrete layers due to the rapid setting, okay. So the retarder can be used to prevent the coal joint formation, and it can also help in increasing the travel time for trucks, okay. So when you have to shift the concrete from batching plant to the site, so if the distance is quite large, so we use the help of retarder, okay. Similarly, accelerator is used in early strength when we require strength very early, okay. Say for example in a repair job, or mainly in cold weather concreting where the rate of hydration is very slow, okay, or in a short grid, because in this case the water cement ratio is very high, and that's why the stiffness will occur, the time required for stiffness occurrence is very high, so we take the help of accelerator, okay. So if we plot slump versus time plot, okay, for the retarder, normal setting and accelerated setting, okay, so we will see that the time the time taken for stiffness, okay, for both retarded and normal setting is almost the same, but the retarded setting is giving high slump for a much bigger time, okay, as compared to the normal setting. And in the case of accelerated setting, what we find is that the stiffness occurs even lesser than half the time that is required for the case of normal setting, okay. So those are the advantages of using retarder and accelerator, okay. So how does now let us see the use of chemical admixture as a water reducer, which we use in that problem, okay. So here, if we see water reducer, they can be, uh, they can act as plasticizer as well as super plasticizer. So they are used to reduce the water demand for a given workability. So basically, its principle is that the water is generally trapped by the cement clinkers or the particles. So what happens is that in the presence of plasticizers, these particles are sparse, okay, cement particles. So this increases the workability, and therefore we can reduce the water content, okay. So effectiveness can be measured in terms of percentage of water reduction, which can be AC for a given dosage and a particular this one slump, okay. Say for example, if 180 kg of water is required in that for example, in that problem, if we see 180 kg was required water for a certain slump without admixture, and when we reduce the water by 20%, still we got the same slump because of the addition of admixture at a certain dosage, okay. So the we can see the use of admixtures, chemical admixture in various ways in this one, in this trial mix plot, okay. So if you see here, this is the base case, okay, 180 360.50832, okay. So here no chemical admixture is used, okay. In case of higher strength, okay, so higher strength, if you see, what is happening is they have reduced the water cement ratio, okay, by using chemical admixture. That is, they have reduced water content, and because they have reduced water content and kept the cement content same, the W by C value reduced. And from the this one plot and the nature behavior as well as Abrams law, we know that as W by C increases, the strength decreases, the strength increases, okay. So we are getting higher strength. In the case of cement saving, what we did is we wanted the same water cement ratio, okay. So because water content was reduced, the cement also got reduced, okay. So we are getting the same strength at a very lesser cement content, so the cement is safe, okay. And in plasticizing action, we want more slump, okay. So more slump, to get that, we are maintaining everything to be same, just we have added the chemical admixture, and using this principle, it has given more workability or slump, okay. So that is the use of chemical admixture as a water reducer, okay. And various other for using as a plasticizer, plasticizing agent, cement, for saving cement, as well as for increasing the strength, okay. So these are the utilities, okay. And also one more utility of using chemical admixture is for air entraining as a air entraining admixture, okay. So these are used in air entraining concrete. So air entrainment is accompanied by increase in workability, and hence it may be required that the unit water content may have to be reduced for a certain workability. So air entrainment, as we studied last class, that again results in the increase of workability, and the range should be between 4 to 10%, okay. So that gives a very good workability and a very good durability factor as well. So that results in more good it results in a good behavior, okay, 4 to 10%. So generally greater than 10 is not good, and in normal concrete it is between 1 to 1.5, okay. So that is the reason why it is important to have between this, and for that we use air entraining agents, okay, admixtures. So the difference between entrained air and entrapped air is basically this entrained air, it basically contains an air distribution which is uniform, okay. So because of that, there is very less chance of this one cracking, shrinkage, okay. And mainly it helps in the as we studied last class, it provides resistance to freezing and thawing and actions, and also it protects from scaling, okay. From dicing soils through peeling off, or spalling, okay. So that is the utility of entrained air, okay. And in the case of entrapped air, that mainly comes from insufficient compaction, okay. So that results in honeycombing and all the other things, and this is non-uniform air distribution, okay. So air entrainment is mainly due to intentional creation with air entraining admixtures, but it has one problem, and that is like we have to compromise with strength, okay. So there is a catch there. So these are the pictures of air entraining as well as the entrapped air. So yeah, other chemical admixtures are also present which can be added for concrete during mixing, and that will reduce or remove the slow the process of corrosion. And one of the chemical admixture which can help is nitrites. Okay, and there is some evidence that presence of these ions in the concrete mix helps in preventing as well as providing additional resistance against reinforcement corrosion. Okay, so such admixtures such as nitrates can be used as corrosion inhibitors. So motivation to use mineral admixtures are mainly the main ways. Okay, so till now we have studied about chemical admixture. So now let us go to mineral admixture. Okay, so mineral admixture is basically used. Okay, so the main reasons for using comes from these reasons, these factors. So one is industrial byproduct utilization, which is again a waste material. Second is a environmental concern, because it is a waste material that will lead to sustainable development. And thirdly, because it is a waste product, so which is free, so it is result in economy in cement consumption. Also, that will, because it is not hydration does not occur, so it will result in reduced heat of hydration. And that may, we have to go through durability considerations for enhancing its purpose, so it may improve the durability as well. And it also can help in giving high strength requirements. Okay, so all those parameters are there based on research, so they can be useful. Okay, so mineral admixtures in concrete, they are used in concrete mixes, and they are used in two ways. Okay, here one thing to note is that in chemical admixture, that is used directly at the time of mixing. Okay, but in case of mineral admixture, that can be used both ways, as a partial replacement, that is at the time of mixing, and also in addition to the cement. Okay, so that is during the time of manufacturing, that is making a blended cement. Okay, so say for example, the PPC, Portland pozzolanic cement. So that is a blended cement which contains a certain percentage of fly ash. Okay, so which is manufactured directly manufactured. It is not required to be mixed at the time of casting. Okay, so that is the difference. One more difference between mineral and chemical. So these two ways we can use mineral admixture, and they help to improve the properties of concrete. And this can be in terms of development of compressive strength, as well as liberation of heat of hydration or any other parameter. Okay, so usually mineral admixtures are basically one of the famous mineral admixture is the pozzolanic material. Okay, so what is pozzolanic material? So those are materials, okay, which basically contain silica and alumina, mainly the silica portion, SiO2, which does not actually have any hydraulic property. That is, they don't react with water. Okay, so they don't react with water directly, so they don't harden. Therefore, they only react with calcium hydroxide. Okay, and thereafter they form products which are similar in nature to that of cement. Okay, cement products like cement hydration products. So this is basically the hydration mechanism of normal cement. So here if you see halide and belite, okay, so they react with water and form CSH gel plus calcium hydroxide, or this is also known as portlandite. Okay, so those are the main products, direct products of hydration. Okay, so that is in the case of cement particles. Okay, but in the case of this one, hydration products of in the case of pozzolanic material, you will see that the silica, that is SiO2, directly reacts with portlandite. Okay, so that will result in the formation of CHH gel. Okay, so here CSH gel is not formed. Okay, silica does not react with CSH, or nor does it provides reacts with water. Okay, it directly reacts with the portlandite in the presence from the which is present from the original cement, and results in the formation of CSH gel. So hydration reactions of pozzolanic material, in other words, if we say the CSH gel is formed in pozzolanic reactions in a two-phase reaction. Okay, first is the CSH, okay, which is from the main hydration. Okay, that results in the formation of CSH as well as CH, and the second CSH gel is formed from the interaction of CH from the main cement and the silica from the mineral admixture. Okay, so from that we can obviously say that the phase of CSH is much richer in the cement uh, or in the concrete and very poorer in CH. Okay, and this is a good thing because the main binding property as well as the strength comes from the calcium silicate hydrate gel, not from the CH. Okay, so lesser is the CH value, more better is the binding property as well as the strength. Okay, so as I discussed just before, this mineral admixture addition, this can be done two ways. Okay, one is at the time of manufacturing. This is called as a blended cement, which is PPC, for example, and second is the using it directly at the time of mixing. Okay, in partial replacement of cement. Okay, which we have discussed altogether. So mineral admixture is basically used in concrete are of three types. Okay, one is very famous. All the three are very famous. One is GGBFS, which is the byproduct of steel. Okay, ground granulated blast furnace slag. Second is the fly ash, which is used in thermal power plants, and third is the silica fume. So this is mainly used in high strength concrete. Okay, so the dosage of mineral admixtures are again based on trial. Okay, so and trial, and we mainly follow the efficiency. Okay, so it is based on the efficiency, which is again got from trial, and the desired result. Okay, in general the range is such. Okay, in slag we can replace by weight 30 to 70%. In terms of fly ash we can replace by 10 to 30%, and in silica it is 5 to 15%. So maximum slag can be replaced. Okay, because it mainly contains calcium as well as silica as well as calcium. Okay, which is lesser in case of fly ash and even lesser in case of silica fume. Okay, so dosage of mineral admixtures, so even it has been found that apart from these ranges also some special literatures have suggested use of mineral admixtures beyond these ranges as well. So for example, in the case of high volume fly ash applications such as in road construction. Okay, so there higher levels of fly ash replacement have been actually used. Okay, but those are beyond this beyond the scope of this subject. And also I feel this is possible because it is not a this one here the safety factor is not that much of an issue. Even if the road construction, if the pavement fails also, no, nothing serious is going to happen. But that is not the case in the construction. Okay, if something happens there will be a lot of casualties. So risk factor is one of the main factors associated with its use also, because ultimately we want strength. Okay, so the dosage of mineral admixture, if we see 50% replacement by slag in a mix containing 400 kg cement, it will mean that 200 kg of cement will be there and 200 kg of slag will be there. Okay, similarly if we are adding 5% additional silica, that means in 400 kg 20 kg of silica fume will be present. Okay, in the cement. So uh, that is possible if the efficiency is 100%. Okay, but because the efficiency will not be 100%, therefore we need to add more. Okay, so that is why the efficiency factor is important. So depending upon the chemical composition of mineral admixture, its reactivity with calcium hydroxide will be different. Okay, so thus the potential to form the required CHS gel would also vary. So the efficiency of a mineral admixture may be defined in terms of its ability to replace cement in a concrete mix. So if 200 kg of an admixture is required to achieve the strength obtained by 100 kg, so its efficiency will be 50%. So like if we want 100 kg, okay, and it's the efficiency of 50% mineral admixture is used, so for 100 kg we have to double it. Okay, so that means we have to divide this by the efficiency. Okay, then we will get the total amount required. So that is the case here. So mix A is having a 350 kg cement. Okay, and mix B is having 300 cement and 100 MA mineral admixture, but both are equivalent. Why? Because 100 is equivalent to 50 kg cement, because it is having an efficiency of 50%. Okay, so both are same. So similarly in previous cases, so in previous examples we used 80 kg having in place of 50 kg cement. Okay, so that meant it was having an efficiency of 50 by 80, which is 62.5%. Okay, so So basically these are the main, as we have understood till now, these are the main constituents, the primary constituents of concrete. Okay, and from that we need to add this mineral admixture or chemical admixture to change the properties as well as the behavior. Okay, so that it suits our needs. Okay, so definitely when we are using mineral admixture and adding it in percentage, okay, therefore then the powder content, okay, that is the binder content, will definitely increase. Okay, if the efficiency is less, and that is definitely less than 100%. Okay, so the ma added will be more than the cement actually replaced, and this increase in we need to let us for example see how much this gets increased. Okay, so based on trial mixes, we have got two constituent proportioning. Okay, proportioning of mixes. So here if you see, in one they have not used mineral admixture, in other they have used. Okay, so both are having the same strength. Okay, so here if you see, in for getting 350, what they have done is they have used 300 of cement and 80 as given in this example only. So 80 having a efficiency of 62.5 is giving 50. Okay, 80 into 60 or 60%, it is around 50 kg. Okay, so if you see, the powder gets increased by around 20.5. Okay, powder as well as the paste. Okay, both are in volume, that is liters, so it is increasing by 20.5 liters, and that is equivalent to around 7% increase of the original value. So the addition of admixture, mineral admixture, results in about 7% or 20 liters increase in the volume of the paste. Okay, so that is the this one, the implication, that is the effect of using this. Okay, and that may also have effect on the water demand. Okay, so that may also be one of the requirements. Okay, but here we are basically confined with the increase in paste. Okay, we are considering water to be consistent because we have assumed this to be we have assumed the efficiency factor. Okay, so we have thought that using 80 80 kg mineral admixture is equivalent to using 0.6 into 80 value of cement. Okay, so that's why we have considered W as consistent, or W by C as consistent. Okay, so based on that, we can see that the in general concrete, it mainly contains about 25% paste. Okay, in terms of volume as well as weight, near about 50% mortar and 40 to 50% of coarse aggregate. And if you see, in case of this one regular mix, this is this one bifurcation of the percentage. And in self compacting concrete, everything is same, only in the case of aggregate there is 8% more fines. Okay, so which results in reduction of coarse aggregate, so that's why it is having a much more workability. Okay, so by with this we will come to the end of this week's lectures. Okay, and now I will briefly go through some problems, and thereafter we can end the discussion. Okay, so let us go through them. So let us consider this problem. In this problem, consider the following mixed proportions of an air entrained concrete which is having 3% air, water 200 kg per meter cube, cement 390 kg per meter cube, and sand 685 kg per meter cube. So let us assume the specific gravity of cement, sand, and coarse aggregate is 3.15, 2.54, and 2.65 respectively. So based on this, which of the following is the best representation of density of concrete? Okay, so we need to basically find the concrete density. Okay, so density in terms of weight, that is kg per meter cube. So if we see here, so weight we don't consider of air. Okay, so it will mainly be water, cement, sand, and aggregate. So here aggregate is missing. Okay, so therefore we need to find out the weight of aggregate. But for finding the weight of aggregate, we need to find the volume of aggregate. And for finding volume, we need to convert all this first into volume using the specific gravity. And along with, we have to consider also the 3% air. Okay, so based on that, we need to find the volume of coarse aggregate, and then again using specific gravity, we need to find all the weights. Okay, in kg, and along with the coarse aggregate, and then we have to add to get the value. Okay, so this is how it has been done, and the result comes up to be 2270. Okay, So 2270 kg per meter cube is the correct answer. So let us go to the second question. In the context of using chemical admixtures in concrete, consider the following statements. Statement 1, chemical admixtures are added directly to cement during the manufacture of cement to avoid compatibility problems. Statement 2, certain chemical admixtures can be added during mixing process to reduce shrinkage at later edges. So, which of the following is true? Statement 1 is true, 2 is false, 1 is false, 2 is true, both are false. Okay? So, just now we discussed like mineral admixtures can be added both ways. Okay, they can be added during the time of manufacturing as well as at the time of mixing, but chemical admixtures are always added at the time of mixing. Okay, they are not added in manufacturing. So statement 1 is false. Okay, and in the second statement it has been said that chemical admixtures, okay, they reduce shrinkage. So chemical admixtures reduces the water content. Okay, and water content is water content is related to the pores. Okay, so more less is the water content, lesser will be the pores generated, and less is the pores generated, lesser will be the shrinkage. Okay, so we can say that because chemical admixture is reducing water, so pore is also changing, and therefore shrinkage is also reducing. Okay, so therefore chemical admixture helps in the reduction of shrinkage. Okay, so we can say that statement 2 is true. So 1 is false, 2 is true, so the second option will be the correct one. So as you can see, 1 is false and 2 is true. So let us go to the third question. In the context of using admixtures in concrete, consider the following statements. Statement 1, accelerators are sometimes used during colder environments to increase both the setting time and the heat of hydration. Statement 2, the dosage of chemical admixtures is usually greater than 4% by weight of cement used. Which of the following is true? Statement 1 is true, 2 is false, 1 is false, 2 is true, both are false. So as you can see, accelerators, they are mainly used to increase the heat of hydration and decrease the time of setting. Okay, so they are mainly used in cold places, or mainly used in short critting, okay, or where we need rapid strength. Okay? So it reduces the setting time. Okay, so therefore statement 1 is false. Okay, and statement 2, the dosage of chemical admixtures is usually greater. So as we discussed, it should be always, it is very minimum. Okay, it is dilute. Okay, so it will be always lesser. Okay, around 1%, or it should be always less than 4%. Okay, so it is around 1%, so therefore it can be greater. Okay, so statement 2 is also false, so both the statements are false. So fourth option will be the correct one. So as you can see, fourth option is the correct option. Okay, so let us see the fourth question. So here, consider the concretes P and Q which have the following composition given in kg per meter cube of the different constituents. It is also known that the specific gravity of cement, fine aggregate, coarse aggregate, and mineral admixture is 3.15, 2.62, 2.75, and 2.91 respectively. So, which of the following is the best representation of the ratio of the volumetric mortar content in mix P to that of the mortar content in mix Q? Okay, so we need to find out what is the volume of mix P divided by volume of mix Q. Okay, so we need to find the ratio. Okay, so basically what we have to do is we have to convert everything which is given in weight into volume using the specific gravities. Okay, and then we have to find the ratio by P divided by ratio of P divided by Q. Okay, so volume of as you can see, volume of this is this much, and volume of this is this much. Okay, so as you can see, if you divide both the ratios, we will get the value to be around 0.96. So 0.96 is the correct answer. Okay, the first option. Then fifth question, consider the concretes P and Q for which the content in kg per meter cube of some of the constituents is given below. So concrete P is having water of 175 kg, cement 350 kg, mineral admixture nil. Q is having X water content, 300 kg cement and 119 kg mineral admixture. So it is given that the strength, it is known that the strength of the two mixes is similar, and that the mineral efficiency of the mineral admixture from the point of view of its ability to replace cement as far as strength is concerned is 65%. Now, which of the following is the best representation of the water content in kg per meter cube for concrete B, X in the table? Assume the specific gravity of cement and the mineral admixture to be 3.15 and 2.95 respectively if required. Okay, so here basically we need to find the value of x. Okay, so x gives the value of water content in q. Okay, so here basically if uh, here as it is mentioned that the strength of the two mixes is similar, right? So because the strength of the two mixes is similar, that means the water content of the two has to be similar. Okay, so water content is equal to w, like water cement, sorry, water cement ratio has to be similar. Okay, so water cement is equal to this one, in p it is w, like water by cement, and in case of q it is water by cement plus 0.65 into mineral admixture, that is 175 equal to 175 175 by 350 is equal to x by 300 plus 0.65 into 119. Okay, so as you can see here we can equate like this, and this gives the value of x which comes around 189. Okay, so 189 is the answer, 189 kg per meter cube. And I think this is the last question. So here two concretes designated as A and B are designed. Mix A is normal concrete, while in the mix B a water reducing admixture is added. So it is known that the cement content is same in both the mixes. Okay, the workability of the mix as measured using the slum test, sorry, was found same for both the mixes. So now which of the following statements can be made regarding the compressive strength of mixes A and B? Strength of mix A is higher than mix B, strength of mix B is higher than mix A, the strength of both the mixes are similar, or conclusive statement cannot be made based on the information available. So if you see here, here it is written that the cement content is same in both the mixes. Okay, so that means in both the mixes the cement has not been changed. Okay, so like the total cement content is similar. Okay, even after using admixture, so it is same, and the workability of the mix as measured using the slum test was found to be as was found same for both the mixes. So definitely the workability of the cement of the workability of the mix was measured using the slum test. Okay, so that was also found the same. Okay, that was also found same for both the mixes. Okay, so that means the this one, because because it is a water reducing admixture. Okay, so that means the this one the water value has decreased in case of B. Okay, so that means because the cement content is same and W is less, so in case of B the W by C value will be lesser. Okay, and from Abram's law we know that lesser is the W by C ratio, higher is the compressive strength. Okay, so therefore as the water content is less in B and the cement content is same in both, so the W by C value of B is lesser than W by C of A. That means compressive strength of B will be higher than compressive strength of A. So that means the strength of mix B is higher than mix A. So the second option will be the right one. So as you can see, the strength of mix B is higher than that of mix A. Okay. So yeah, so with this we come to the end of today's discussion. So yeah, if you have any questions, you can ask. Do you have any questions? Okay. Okay, so if you don't have any questions, so let us end this meeting today. Let us meet again next Sunday, and we will carry forward our discussion. And we will then go inside. I think we will start our special concretes. Okay, so from next class, I think we will be starting our this one. Our main topics will be started from next class, and we will go into more detail. Okay, and the characteristics and behavior of the mechanisms and all the processes, okay, involved. So I think till now everything is clear and you have understood. So with this I would like to end today's meeting. Okay, thank you.